702.
The Naked Scientist.
21 minutes to 3 o'clock, time for the Naked Scientist. Get in touch with us on 011 883 0702 and the WhatsApp line 072 702 1702. Dr. Chris Smith, happy Monday. How are you doing?
Oh, I'm very good. Thank you very much. How about yourself?
I am doing very, very well, and I'm excited to ask you a question. Earlier on, we were chatting in our Parenting and Parents feature around reparenting oneself. And one of the parts of the conversation led to the part of unmet needs, to which our clinical psychologist was sharing that sometimes you think you are in love or you love somebody now as it's manifesting within your romantic relationship, when other times it's an attachment. Is there any sort of science or research that has been done where it can show in the brain the difference between what love is and what an attachment is, or a trauma bond, or anything that love is not?
That's an interesting question. I haven't been asked that before, and I never really thought about it in those terms, because I've always sort of regarded love as a special relationship between close individuals, but other people can have a strong bond and not necessarily be in love, can't they? If we think about what happens to make a bond between, say, a mother and a baby, or between two couples, in fact, unromantically, you can distill this down to neurochemistry and what the brain is doing. And this has been studied in quite a lot of detail. There is a chemical in the brain called oxytocin, which is produced by your pituitary gland, and it comes out from the back part of the pituitary in response to a couple of things. One of them is when there is stimulation to the nipple when the baby first starts to suckle. And this has two effects. One, it causes blood vessels to constrict. It also produces sensations of pleasure, and it acts in the brain to effectively create a powerful association or bond with that baby. So what many people argue is that when a baby's first born, this reflex, the breast milk letdown reflex, occurs because the mum or the midwife or whoever puts the baby straight to the breast. The baby suckles. That's good for the baby. It needs fluid. It needs nutrition. But it also triggers this reflex in the mum's brain that releases oxytocin. The oxytocin goes into the brain and triggers a bond to the baby. But also it goes around the mum's bloodstream, goes to the uterus and makes the uterus contract, which reduces the risk of any blood loss. And so it has this double whammy beneficial effect. So what's the other example of this happening? Well, when a person has a sexual climax, an orgasm, you also produce a lot of oxytocin in the brain. And so the same mechanism that bonds a mum to a newborn also bonds a couple together who have sex together and share climaxes together. So effectively, you're using the same wiring, the same neurochemistry to create a bond that's long-term, long-lasting. And we also know that oxytocin drives an experience or a perception of trust between individuals. And you can do experiments where you can expose a person artificially to oxytocin, and then you can gauge the trustworthiness or their view of the trustworthiness of a third party, and it goes up in the presence of oxytocin. So when we're talking about attachments and bonds and being in love, I think all these things all center on this set of pathways in the brain that are linking your pleasure center, your emotional centers, and this important neurochemical oxytocin.
Oh, you always have an answer, though. Even though no one's ever asked you, Dr. Chris, you always have an answer.
Well, look, science is all about questions, and a lot of the aspect and the practice of science is taking what we do know and coming up with hypotheses to test what we might want to know or how we think things are working, or building things up from first principles. Now, biology is a bit harder to do that with than, say, physics, where there are rules of physics that are immutable across the universe, and so what works here works on Mars and it works in the Andromeda galaxy. Not the same for biology, but many of the principles are the same. And so you can take what we do know and say, well, how should this apply speculatively under these circumstances? And so that's what you're sort of asking me to do, and that's my speculation.
Absolutely love it. Thank you so much, Doctor. A question says, afternoon, Dr. Nrelebogile. What animal is the fearless honey badger scared of? That's from Holla in Kempton Park. I'm so curious as to where that question
Yeah, where
came
did it
from.
come from?
What
Well,
National Geographic show were you watching?
well, in my experience, they're not even scared of us, are they? Because I mean, I was on a safari in Zambia, and I got woken up every single night, and I thought someone was raiding our camp, and one of the guides said, "No, just the honey badgers. They've discovered where the kitchen is. They've discovered where the food is locked up in a locked cupboard, and they are quite good at getting at it. And so they were making a hell of a ruckus trying to get through a metal door to get at the food. So they're not even scared of us. They're not scared of a noise. So I don't know what preys on a honey badger, but they're pretty fearsome, aren't they? I mean, they're quite well armed, these things, and they're strong. So I think they haven't got much to fear from many things, to be perfectly honest. But I tell you what, I will go and look at what picks on honey badgers, and I'll bring the information back next week.
I would be fascinated to find out that if it has predators but is not afraid, like, is there such a thing as a mammal that has no fear, even though it's got protective mechanisms built within it?
I think all animals have the ability to feel fear. And the reason I'm doing what I said at the top of the show again, but the reason is that their brains are like our brains. They have a structure in the brain which is a fear center, which, when activated, will elicit sensations of alarm and defensive maneuvers. Now, when you activate our amygdala, which is in our temporal lobe on each side of the brain, it makes us feel anxious, nervous, scared, panicky, and also it activates the fight or flight reaction. It makes all your hairs stand on end, it makes your pupils open up, it makes your blood pressure go up, it makes your heart race. It basically gets you ready to fight someone or run away from them. And many animals, in fact all animals that I know of, have the same sort of overall broad brain structure that we do. They have this structure, and I think it will do broadly similar things in them. So I think every animal has the ability, because we at the end of the day have evolved from simpler animals to have the brain structure we do. So I think it's very likely that we inherit our ability to feel fear and alarm and perceive risk and threat and react to it in the way we do from our animal ancestors and relatives. And so all animals have this ability because it's how they make sure they don't turn into someone else's lunch, and that they also protect their young.
12 minutes to 3 o'clock. We continue with the Naked Scientist. 011 883 0702. The WhatsApp line 072 702 1702. We go to the lines. Alistair in Lyndhurst. Go ahead, Alistair.
Dr. Chris, can you explain to me, if you've got a racing car going around the track at 400 kilometers an hour, how do those pistons fire so rapidly? In other words, they become like machine gun bullets to the top of the cylinder and back again to combust. How does it do it so smoothly without any mishaps at a high speed, and it indefinitely you could go on?
Yeah, I know, it's amazing, isn't it, when you think how incredible these engines are, because these engines tuned up for racing are doing that at 10,000 RPM.
But even
revs
normal,
per minute.
even a normal,
Yep.
even a normal car.
Yeah, in your normal petrol engine, they're going a lot faster than a diesel engine, which revs much lower, usually up to about 3 or 4,000 revs a minute. But yes, the way this is done is with very careful machining and balance. So if you think about what's going on in an engine, it's a block of metal and it has a number of cylinders, commonly 4. Some engines have more. The cylinder, each one, has a piston in it. The piston is a round shape which has got rings that seal it inside that hole in the block. And the piston has, coming out of the bottom of it, what's called a conrod. The conrod is articulated on the piston, so it can swing backwards and forwards. And it goes down to a shaft that runs the full width or length of the engine, which is called the crankshaft. And the conrod is attached via a very special clamp and a set of bearings onto that. And as the crankshaft goes round, because the engine's going round, because the crankshaft is eccentric, in other words, it's not just a round shaft, it's a shaft where it's got one bit is up in the air and the one next door is down below. As it turns round, it means the piston goes up and down because the conrod flexes backwards or swings backwards and forwards to accommodate the side-to-side movement. This is very carefully machined to make sure, and it's all supported by bearings, that it runs very smoothly with very low resistance, and that this can happen without any kind of the piston hitting the top of the engine or hitting the bottom of the engine. You then do that for each of the pistons, and they're all set up so that they are going up and down at different times. And most engines have a firing sequence of something like cylinder 1 fires, then cylinder 3 and 4 fire, and then it comes back and number 2 fires, 1, 3, 4, 2. It's quite a common firing sequence. And what they do is that balances the forces inside the engine and on the crankshaft, so that you don't get massive resonances and vibration, so that as one thing's firing, something else is relaxing and exhausting and so on, and that gives you the smoothest run. And with good oils to lubricate everything, because it's so low resistance and so carefully balanced, when new and not worn out, it will run incredibly fast with very low losses and tolerate very high rates of RPM.
Thank you so much, Alistair, for your question. We then go to Kabelo from Pretoria. Go ahead, Kabelo.
Good afternoon, Lebohile. The question that I always wanted to ask Dr. Chris is that were humans designed in codes, were they meant to consume meat? Because when you look at our teeth, they are not as sharp as those animals that eat meat. And then we are the only animals that have to cook meat before we can consume it. So were we designed to eat it or not?
I'll be curious to know, Kabelo, are you a vegetarian or you are a meat lover?
No, I'm an omnivore. I consume everything.
He consumes this program, doesn't he? Which says it all.
Okay.
The answer to this, you're quite right to look at the teeth, because at the end of the day, teeth evolve to serve a purpose, which is not just defense, but also to make calories available from what we eat. And if you look at the structure and shape of teeth, that gives you a clue as to what an animal spends its time eating. An elephant's teeth are set up as enormous great crushing stones like millstones to grind up very tough plant material and liberate tiny numbers of calories from large amounts of plant material. So they're set up to grind stuff up. A cow's teeth are set up with lots of ridges of harder enamel and valleys of softer dentine. Horses are the same, and they grind against each other to smash up grass so that they can initially break the grass down to make it easy to swallow, and then when they chew the cud, grind away at the cud, which is the fermenting grass from their stomach, so that they can liberate more calories and also feed that soup to bacteria, which then nourish the cow. The cow eats bacteria. It doesn't eat grass. It feeds bacteria grass, and then the bacteria make the calories for the cow. In us, our ancestors, if you go back 6 million years or so, that was the last time we shared an ancestor with a chimpanzee, for example. Animals that eat a lot of plant matter, like other primates and so on, have teeth of a very specific shape and size, and they are clearly well adapted to eating a lot of plant matter. And our fossil ancestors, if we go back in time to Australopiths, for example, South Africa very famous for having an extremely rich fossil record of this aspect of human and early human and human ancestor evolution. They also have teeth which are set up to clearly derive a lot of calories from plants. But our lineage, Homo, comes along a few million years ago, maybe 2 million years ago, begins to come in, and you see the teeth are clearly different, demonstrably different from these Australopiths. And the teeth are smaller, and they're clearly adapted to not just eat plant things, but to eat a range of things. And so it looks like even from the very earliest times, we were eating a balanced and varied diet, which wasn't just plant dominated and wasn't just meat dominated. We didn't have teeth that looked like a big cat or a dog, and we didn't have teeth that looked just like a gorilla. So we were clearly deriving calories from a range of different sources. And therefore, it's reasonable to assume that our biology and our evolution since has been along the lines of catering for a mixed diet. And therefore, we regard the human diet as appropriately, or most appropriately, an omnivorous one, a bit like you're saying, where you eat a bit of everything, but you don't have to eat just one thing.
Thank you so much for that question. We go to Rueda. Go ahead, Rueda.
Hi, good afternoon, doctor. Bone marrow cancer. Why are there absolutely almost no symptoms in the patient? Only a few weeks, the patient dies, and when they do the test, then thereafter they find out it's bone marrow cancer. Is this the only cancer that sneaks up on the patients?
Hi, Rueda. I'm sorry if this has affected you personally or someone close to you. And you're quite right to say that this does tend to present late. But it's not the only cancer that does. There are other cancers and malignancies that present late. And, for example, pancreatic cancer. is a classic one. And usually these sorts of cancers that present late because they can get quite advanced before they compromise a major system that gives the game away. Now, with the bone marrow, inside your long bones, like your thigh bones or your upper arm bones or your pelvis, sternum, you have a cavity. And the bone in there looks spongy when you cut through the bone and look at it. And in that spongy cavity, which you see when you get bones from the butcher's shop, it's the marrow cavity, it's rammed full of stem cells. These are called hematopoietic stem cells. They are stem cells that, unlike a skin stem cell that would make skin, these stem cells make the blood cells. These include the red blood cells that carry oxygen around the body, the white blood cells, the lymphocytes that fight infection, and also you have platelets, the megakaryocytes that make platelets that help blood to clot. These are right through the bone marrow, and there are huge populations of them. And you don't generally have problems until you lose a significant proportion of them. So the cancer, which starts as an abnormal group of these stem cells proliferating out of control, can actually get quite advanced through the bone marrow before it's pushed out enough of the healthy cells and stops them doing their job adequately. And that then leads to not enough red blood cells, that's anemia, or too many white blood cells, and that makes the blood sticky and can cause problems. So in other words, you don't tend to see problems until the cancer's quite far advanced. But that doesn't mean it's game over, because haematologists these days are amazing doctors and they can do wonderful things. We've got drugs that very quickly will get rid of a lot of these cancer cells, and we can even use radiation to just zap the cancer cells. The key thing is giving a person back healthy stem cells that can repopulate the bone marrow and provide for that person the right elements that the blood needs. And that can sometimes be the problem. And also people can sometimes get very nasty infection, because when the bone marrow gets taken over in this way, the immune system goes off kilter for a while, and that can leave the person open to all kinds of nasty infections. And sometimes it's that claims their life rather than the underlying bone marrow cancer. But if that can be surmounted and a donor can be found, a person with the right bone marrow features that match the genetics of the person affected, then you can blitz the unhealthy bone marrow, you can put in stem cells collected from another person, they will naturally find their way back to the bone marrow and reproduce a new bone marrow that's healthy for that person, and it saves enormous numbers of lives all around the world every single year. It's amazing technology.
Thank you so much. We're going to have to leave it there. Dr. Chris Smith, back together next week.